Section 4 of the atomic bombings of Hiroshima and Nagasaki. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, visit LibriVox.org. The atomic bombings of Hiroshima and Nagasaki by the Manhattan Engineer District, June 29, 1946. Section 4, including total casualties and the nature of an atomic explosion. Total casualties. There has been great difficulty in estimating the total casualties in the Japanese cities as a result of the atomic bombing. The extensive destruction of civil installations, hospitals, fire and police department, and government agencies, the state of utter confusion immediately following the explosion, as well as the uncertainty regarding the actual population before the bombing, contribute to the difficulty of making estimates of casualties. The Japanese periodic censuses are not complete. Finally, the great fires that raged in each city totally consumed many bodies. The number of total casualties has been estimated at various times since the bombings with wide discrepancies. The Manhattan Engineer District's best available figures are Table A, Estimates of Casualties. Pre-raid population: Hiroshima 255,000, Nagasaki 195,000. Dead: Hiroshima 66,000, Nagasaki 39,000. Injured: Hiroshima 69,000, Nagasaki 25,000. Total casualties: Hiroshima 135,000, Nagasaki 64,000. The relation of total casualties to distance from X, the center of damage, and point directly under the airburst explosion of the bomb, is of great importance in evaluating the casualty-producing effect of the bombs. This relationship for the total population of Nagasaki is shown in the table below, based on the first obtained casualty figures of the district. Table B, relation of total casualties to distance from X. Distance from X in feet, 0 through 1,640. Killed, 7,505. Injured, 960. Missing, 1,127. Total casualties, 9,592. Killed per square mile, 24,700. Distance from X in feet, 1,640 through 3,300. Killed, 3,688. Injured, 1,478. Missing, 1,799. Total casualties, 6,965. Killed per square mile, 4,040. Distance from X in feet, 3,300 through 4,900 feet. Killed, 8,678. Injured, 17,137. Missing, 3,597. Total casualties, 29,412. Killed per square mile, 5,710. Distance from X in feet, 4,900 through 6,550, killed 221, injured 11,958, missing 28, total casualties 12,207, killed per square mile 125. Distance from X in feet 6,550 through 9,850 feet, killed 112, injured 9,460, missing 17, total casualties 9,589, killed per square mile 20. No figure for total pre-raid population at these different distances were available. Such figures would be necessary in order to compute percent mortality. A calculation made by the British mission to Japan and based on a preliminary analysis of the study of the Joint Medical Atomic Bomb Investigating Commission gives the following calculated values for percent mortality at increasing distances from X. Table C, percent mortality at various distances. Distance from X in feet, 0 through 1,000 feet, percent mortality, 93%. Distance from X, 1,000 through 2,000 feet, percent mortality, 92%. Distance from X, 2,000 through 3,000 feet, percent mortality, 86%. Distance from X, 3,000 through 4,000 feet, percent mortality, 69%. Distance from X, 4,000 through 5,000 feet, percent mortality, 49%. Distance from X, 5,000 through 6,000 feet, percent mortality, 31.5%. Distance from X, 6,000 through 7,000 feet, percent mortality, 12.5%. Distance from X, 7,000 through 8,000 feet, percent mortality, 1.3%. Distance from X, 8,000 through 9,000 feet, percent mortality, 0.5%. Distance from X, 9,000 through 10,000 feet, percent mortality, 0. It seems almost certain from the various reports that the greatest total number of deaths were those occurring immediately after the bombing. The causes of many of the deaths can only be surmised, and of course, many persons near the center of explosion suffered fatal injuries from more than one of the bomb effects. The proper order of importance for possible causes of death is burns, mechanical injury, and gamma radiation. Early estimates by the Japanese are shown in D below. Table D. Cause of immediate deaths. City of Hiroshima. Cause of death, burns, 60% of total. Falling debris, 30% of total. Other, 10% of total. City of Nagasaki. Burns, 95% of total. Falling debris, 9% of total. Flying glass, 7% of total. Other, 7%. The nature of an atomic explosion. The most striking difference between the explosion of an atomic bomb and that of an ordinary TNT bomb is, of course, in magnitude. As the President announced after the Hiroshima attack, the explosive energy of each of the atomic bombs was equivalent to about 20,000 tons of TNT. But, in addition to its vastly greater power, an atomic explosion has several other very special characteristics. Ordinary explosion is a chemical reaction in which energy is released by the rearrangement of the atoms of the explosive material. In an atomic explosion, the identity of the atoms, not simply their arrangement, is changed. A considerable fraction of the mass of the explosive charge, which may be uranium-235 or plutonium, is transformed into energy. Einstein's equation E equals mc squared shows that matter that is transformed into energy may yield a total energy equivalent to the mass multiplied by the square of the velocity of light. The significance of the equation is easily seen when one recalls that the velocity of light is 186,000 miles per second. The energy released when a pound of TNT explodes would, if converted entirely into heat, raise the temperature of 36 pounds of water from freezing temperature, 32 degrees Fahrenheit, to boiling temperature, 212 degrees Fahrenheit. The nuclear fission of a pound of uranium would produce an equal temperature rise in over 20 million pounds of water. The explosive effect of an ordinary material, such as TNT, is derived from the rapid conversion of solid TNT to gas, which occupies initially the same volume as the solid. It exerts intense pressures on the surrounding air and expands rapidly to a volume many times larger than the initial volume. A wave of high pressure thus rapidly moves outward from the center of the explosion and is the major cause of damage from ordinary high explosives. An atomic bomb also generates a wave of high pressure, which is in fact of much higher pressure than that from ordinary explosions, and this wave is again the major cause of damage to buildings and other structures. It differs from the pressure wave of a blockbuster in the size of the area over which high pressures are generated. It also differs in the duration of the pressure pulse at any given point. The pressure from a blockbuster lasts for a few milliseconds. A millisecond is 1/1000th of a second only. That from the atomic bomb for nearly a second, and was felt by observers both in Japan and in New Mexico as a very strong wind going by. The next greatest difference between the atomic bomb and the TNT explosion is the fact that the atomic bomb gives off greater amounts of radiation. Most of this radiation is light of some wavelength, ranging from the so-called heat radiations of very long wavelength to the so-called gamma rays, which have wavelengths even shorter than X-rays used in medicine. All of these radiations travel at the same speed. The speed of light, is 186,000 miles per second. The radiations are intense enough to kill people within an appreciable distance from the explosion, and are in fact the major cause of deaths and injuries apart from mechanical injuries. The greatest number of radiation injuries was probably due to the ultraviolet rays, which have a wavelength slightly shorter than visible light, and which caused flash burn comparable to severe sunburn. After these, the gamma rays of ultra-short wavelength are most important. These cause injuries similar to those from overdoses of X-rays. The origin of the gamma rays is different from that of the bulk of the radiation. The latter is caused by the extremely high temperatures in the bomb, in the same way as light is emitted from the hot surface of the sun or from the wires of an incandescent lamp. The gamma rays, on the other hand, are emitted by the atomic nuclei themselves when they are transformed in the fission process. The gamma rays are therefore specific to the atomic bomb and are completely absent in TNT explosions. The light of longer wavelength, visible and ultraviolet, is also emitted by a TNT explosion, but with much smaller intensity than by an atomic bomb, which makes it insignificant as far as damage is concerned. A large fraction of the gamma rays is emitted in the first few microseconds, millionths of a second, of the atomic explosion, together with neutrons which are also produced in the nuclear fission. The neutrons have much less damage effect than the gamma rays because they have a smaller intensity and also because they are strongly absorbed in air and therefore can penetrate only to relatively small distances from the explosion. At 1,000 yards, the neutron intensity is negligible. After the nuclear emission, strong gamma radiation continues to come from the exploded bomb. This generates from the fission products and continues for about 1 minute until all of the explosion products have risen to such a height that the intensity received on the ground is negligible. A large number of beta rays are also emitted during this time, but they are unimportant because their range is not very great, only a few feet. The range of alpha particles from the unused active material and fissionable material of the bomb is even smaller. Apart from the gamma radiation, ordinary light is emitted, some of which is visible and some of which is the ultraviolet ray, mainly responsible for flash burns. The emission of light starts a few milliseconds after the nuclear explosion, when the energy from the explosion reaches the air surrounding the bomb. The observer sees, then, a ball of fire which rapidly grows in size. During most of the early time, the ball of fire extends as far as the wave of high pressure. As the ball of fire grows, its temperature and brightness decrease. Several milliseconds after the initiation of the explosion, the brightness of the ball of fire goes through a minimum. Then it gets somewhat brighter and remains at the order of a few times the brightness of the sun for a period of 10 to 15 seconds for an observer at 6 miles distance. Most of the radiation is given off after this point of maximum brightness. Also, after this maximum, the pressure waves run ahead of the ball of fire. The ball of fire rapidly expands from the size of the bomb to a radius of several hundred feet at 1 second after the explosion. After this, the most striking feature is the rise of the ball of fire at the rate of about 30 yards per second. Meanwhile, it also continues to expand by mixing with the cooler air surrounding it. At the end of the first minute, the ball has expanded to a radius of several hundred yards and risen to a height of about 1 mile. The shock wave has by now reached a radius of 15 miles, and its pressure dropped to less than 1/10 of a pound per square inch. The ball now loses its brilliance and appears as a great cloud of smoke, the pulverized material of the bomb. This cloud continues to rise vertically and finally mushrooms out at an altitude of about 25,000 feet, depending upon meteorological conditions. The cloud reaches a maximum height of between 50,000 and 70,000 feet in a time of over 30 minutes. It is of interest to note that Dr. Hans Bethe, then a member of the Manhattan Engineer District on loan from Cornell University, predicted the existence and characteristics of this ball of fire months before the first test was carried out. To summarize, Radiation comes in two bursts: an extremely intense one lasting only about 3 milliseconds, and a less intense one of much longer duration lasting several seconds. The second burst contains by far the larger fraction of the total light energy, more than 90%. But the first flash is especially large in ultraviolet radiation, which is biologically more effective. Moreover, because the heat in this flash comes in such a short time, there is no time for any cooling to take place, and the temperature of a person's skin can be raised 50 degrees centigrade by the flash of visible and ultraviolet rays in the first millisecond, at a distance of 4,000 yards. People may be injured by flash burns at even larger distances. Gamma radiation danger does not extend nearly so far, and neutron radiation danger is still more limited. The high skin temperatures result from the first flash of high-intensity radiation and are probably as significant for injuries as the total dosages which come mainly from the second, more sustained burst of radiation. The combination of skin temperature increase plus large ultraviolet flux inside 4,000 yards is injurious in all cases to exposed personnel. Beyond this point, there may be cases of injury, depending upon the individual's sensitivity. The infrared dosage is probably less important because of its smaller intensity. End of section 4 of the atomic bombings of Hiroshima and Nagasaki.